Okay, thank you very much, Colin, and it's great to be here. Yeah, so I'm going to talk about imaging all the sky all the time, searching for radio exoplanets, and I have this ridiculously over-stylized image here of some of the motivation for why I'm doing that. Before I get into the topic, I want to just mention things that I work on and my group works on. If you want me to discuss any of this other work, let me know. So my main science interests are the magnetic fields of stars, planets, and brown dwarfs, understanding their magnetospheric processes, and also understanding how the activity of a star can impact the atmospheres of a planet, but also the radio transient sky, building systematic surveys to survey the sky, looking for radio transient sources. And this includes following up advanced LIGO Virgo sources, and I'll discuss some of this tomorrow at Princeton, I believe. And to do this, my group builds instrumentation, primarily at the Owens Valley Radio Observatory, which is about 4.5 hours north of Pasadena, and that includes the Avro LWA, which I'll mention today, and then the Deep Synoptic Array is a new FRB localization experiment that just got funded via the NSF MSIP program. I'll mention that tomorrow. And then I also build some optical instrumentation for Palomar. Okay, so back to my title slide that I've now sneakily changed to say extrasolar space weather, because I'm not just interested in the magnetic fields of exoplanets. I'm interested in the activity of stars and how to trace things like coronal mass ejections and their impact on exoplanets. Before I talk about extrasolar space weather, though, I want to talk about our own space weather, and here I'm just showing the last major space weather event we had, which was in September 2017. There was an X9.3 class flare on the Sun, the largest solar flare in about 12 years. And associated with that flare, there was a very large coronal mass ejection, as seen here in Thomson scattered light via SOHO. And you can see the CME has kind of a halo effect to it, and that's because it's partially traveling in our direction, which occasionally happens, and when it does, it can affect our local space environment. And based on that event, there were predictions of a very large geomagnetic storm. The original prediction was a G3 class storm, and when it eventually hit, it ended up being a G4 storm, a very severe storm. There were auroras seen right down into the northern United States. And this fact that it was a G4 rather than G3 shows you that space weather prediction is still an imperfect process. And these kind of events can have lots of effects. It can affect, for example, communication. It can affect any satellites that are orbiting at the time, or in fact, if there are any astronauts in space at the time, it's a risk. It can also impact power grids. The largest event that's happened in the last 200 years is an event called the Carrington event in 1859. And if it struck today, the DOE projection of potential impact is a couple of trillion if it hit the US power grid. So it can have severe impact. What I'm interested in is the impact on longer timescales. And here I'm showing an illustration of the MAVEN mission to Mars. And the effects that we are interested and concerned about are twofold. When you have a very large flare, you have high energy X-ray and ultraviolet radiation flux. And that can lead to things like photoionization, but also the heating of the thermosphere beyond the exosphere. And then secondly, the large volume of particles and magnetic fields that are ejected during a coronal mass ejection. And these can directly impact the atmosphere of a planet. In fact, what the MAVEN mission to Mars measured was the amount of atmospheric loss during a CME, which suggested that the loss of Mars' atmosphere early in its life was actually due to this process, due to coronal mass ejections. We also think, in the case of Venus, which of course has a thick and dense atmosphere, that it had a role there as well also, because we think that the water content of Venus may have been removed via a similar process. Of course, the Earth maintains a robust atmosphere and a biosphere, and the reasons for that are we think manifold. But one possible role is the presence of a large-scale and stable magnetic field, although the actual implications of that for atmospheric retention are still being investigated. So we know that magnetic activity can redefine atmospheric retention and habitability. We've seen an example in our own solar system. We know that Mars, for example, had a magnetic field early in its life, and that when the core froze out, it lost that magnetic field. And we know that stellar activity can, in fact, play that role. And we think that the magnetic fields of planets may play an important role as well also. So zooming a bit further out, here's a census of stars out to about 8 parsecs. And you often hear the term that the sun's an average star. Well, in fact, it's much larger than an average star. Most stars are much smaller, and the population is dominated by M Dwarves. There are 157 M Dwarves in this relatively complete sample out to about 8 parsecs, compared to just 8 G dwarfs. And of course, M Dwarves are a very exciting topic right now in exoplanets, because we know that small planets are frequent around M dwarfs. They dominate planetary demographics, and rocky planets are particularly frequent around M dwarfs. So much so that the nearest habitable planet likely orbits an M dwarf at 2.6 parsecs, and the nearest transiting habitable planet likely orbits an M dwarf, at about 5 or 6 parsecs. And of course, TESS is launched and is on the search now for this population. And it's of particular interest because these planets present really high probability examples of what we can try and do with high contrast spectroscopy in the next few decades, for example with JWST, to try to constrain atmospheric content on these planets. Okay, and a couple of really nice examples, of course, of the last few years include the TRAPPIST-1 system, 7 planets orbiting a very small star, TRAPPIST-1, an M8 star, and of course the nearest star, Proxima Centauri, we think also has a possible rocky planet. Now, sorry? Yes, right. These are high-res photographs from a mission sent recently to TRAPPIST-1. A couple of issues in the context of activity is that a big role, we think at least, in the role of activity is the fact that the habitable zone for an M dwarf is of course much closer than the case of a G dwarf at the Sun, which of course is at 1 AU. For an M dwarf, it's much closer in to maintain the same bolometric flux on the planet, and in fact TRAPPIST-1 is much closer again. And the effect of flares and CMEs is that the flux hitting the system is a factor of the ratio of these two squared higher, right? And we know that M dwarfs flare, by the way. They flare to a much larger degree and much higher degree than we see for the Sun. We don't yet have any information, unfortunately, about coronal mass ejections, though. The other effect is the activity lifetime of M dwarfs. So the Sun was a very active star when it was young. It was a rapid rotator, maintained a much stronger magnetic field. It maintained a bright X-ray corona. In fact, it was about 1,000 times more luminous in X-rays than it is now when it was very young. But due to a very strong stellar wind, it lost angular momentum and spun down. And of course, rotation is what's driving the dynamo and what powers magnetic field activity. It spun down pretty rapidly to be a much more well-behaved middle-aged star. M dwarfs, by comparison, remain petulant for a much longer period of time. Here's the activity lifetime of M dwarfs as a function of subclass. And we see that as you get into the mid and late M dwarfs, they can remain active for many gigayears. And of course, one example would be Proxima Centauri, which is about M5.5. And its expected activity lifetime is many gigayears. And it is, in fact, still quite an active star. So to summarize, the picture I'm trying to understand here is how the activity, and particularly the coronal mass ejections of stars, particularly M dwarfs, might play a role in dominating or at least affecting habitability for these planets, and how important it might be for rocky planets to maintain a large-scale and stable magnetic field. Another in situ movie taken. Okay. Sure.
Are coronal mass ejections always associated with flares?
No, there's not a one-to-one correlation. In fact, the mechanism or connection between the two is poorly understood. We know that, well, almost every very large flare is a coronal mass ejection, and the mechanical energy of that CME is typically related to or correlated with the energy in the flares. So that's a relation we understand for the Sun, but extrapolating up to M dwarfs, the flares are 3 or 4 orders of magnitude more energetic, and we've no data on the CMEs. And an important part of that is that the field topology of M dwarfs we know is very different to what we see with the Sun. The Sun has an alpha mega dynamo, and it has a weak poloidal field that gets wrapped and twisted, and we have an equatorial, almost toroidal field structure. Magnetic fields of M dwarfs have been measured and have been mapped actually via Zeeman Doppler imaging, and in those cases we see very often large-scale, stable, strong dipole fields, right? And how that affects, it won't affect the radiation flux, which will be isotropic, but the large-scale particle flux from a CME may be trapped or redirected, and that's a big and important question we have to understand. So how do we try to trace things like coronal mass ejections and the presence of large-scale fields? We can do this via low-frequency radio emission, and I'll give examples how that works within our own solar system. Remote sensing of CMEs first I'll look at, and how we look at CMEs traditionally for the Sun, of course, is via Thomson scattered light, and we see this has been done since the early 70s. This is not possible, of course, for nearby stars because the inner contrast ratio is just not an option. You'd need a coronagraph, that will be orders of magnitude better in inner working angle than we can currently perceive. How we can, however, remotely sense these coronal mass ejections is via bright luminous radio emission. Here's an example of what we call a type 2 radio burst. Here I'm showing frequency versus time. And we see very bright radio emission very often associated with fast coronal mass ejections. And what we're seeing is, in fact, plasma radiation, a coherent process produced at the local plasma frequency, so it traces density. And what you typically see for a type 2 burst is a sweep across the time frequency plane. And that just basically traces the motion of the shock from that CME as it travels outwards. The radio emission is produced at the shock. It's incredibly bright. It can have brightness temperatures of 10 to the 15 Kelvin. And it basically traces the velocity of that ejection. How bright can these type 2 radio bursts get? Well, the brightest burst we've seen from the sun was in 1947. It's associated with this particular spot group here, which is the largest spot group seen in the sun that we're aware of. And here is just showing the size of Jupiter and Earth for scale. This is not a transit, if anyone thinks it is, for many reasons. The bursts are mostly confined to low radio frequencies. This particular giant type 2 burst reached 10 to the 11 Janskys, which those of you that speak radio units, that's very, very loud, very, very bright. In fact, it's the brightest ever detected extraterrestrial radio emission. That's extremely bright, but it's also fairly rare. For context, if you were, sitting on a planet orbiting, Alpha Centauri, and you happen to be pointing towards the Earth with a radio telescope comparable to what we have with our current generation of instrument, you'd easily detect this. But that's not the issue. The issue is when, all our current generation of radio telescopes, we point them towards nearby stars. You need to monitor. In the same way for the sun, we have a suite of space-based and ground-based instruments that are permanently pointing towards the sun. And our paradigm for observing stars for activity is we point for an hour or two at a time and think that captures the activity of a star. It doesn't. You have to build a system that can monitor nearby stars for space weather to try to capture this kind of event. And my group's been involved in doing the former, which is targeting nearby stars, looking for radio bursts. Here's an example of a paper that recently appeared where we took the VLA, the Very Large Array in New Mexico, which is still the largest and most sensitive radio telescope, and targeted a bunch of nearby M Dwarves to try and get some constraints on what kind of radio burst phenomenology we see and how it compares to what we see for the sun. And here I'm showing just time versus frequency, and the color plot represents intensity. And here's an example of 3 very well-known flare stars, and we see a wide range of phenomenology. We actually tried to go as wide in frequency as we could by subarraying the VLA into 3 subarrays at different frequencies to try to capture this behavior. And we see lots of really nice structure, including one that's kind of like what we see for type 3 bursts from the sun. But we do not see anything like type 2 bursts. We do not see that characteristic sweep across the time frequency plane indicative of a shock wave propagating outwards. And that may be because, like I suggested, the M Dwarves have a different field topology. But it also might be because we're observing at too high a frequency. You need to go, in the sun case, solar case, typically below about 100 megahertz. And this is at gigahertz frequencies where the VLA is sensitive. So I think the key point here, we have many examples of radio bursts which are indicative of effects that, like what we see in the sun, but no clear evidence for a CME-like shock. Now I want to talk briefly about the exoplanet case. What kind of radio emission do we see from exoplanets in our solar system? Yeah? Sorry?
How well do you know the densities?
In the case of the sun?
No, not because of sun. That's actually much better known. But for some of the things that you just showed,
Independently or from the radio emission?
independently.
Independently, you can try and get constraints from X-ray observations. And
Not seeing it because it's so sensitively dependent on both magnetic fields as well as local density.
so in this case, the actual mechanism is not dependent on magnetic fields. If you're looking for the same mechanism as we're seeing in the sun, there's another mechanism that does depend on magnetic fields, which is the electron cyclone maser. And we think that actually what we're seeing here is mostly the electron cyclone maser. I think it's the key thing here is we have no evidence of plasma radiation. Exactly, yeah. Exactly, yeah. That's right.
So you have enough of a range that you can actually scan and see it's insensitive to that. That's what makes you say that you're not seeing.
That's right. The key thing here is that previous observations are all very narrow band, limited by previous generations of radio telescopes. And we're trying to find ways to really probe a large fraction of the time frequency plane to look for the characteristic, motion across that plane indicative of a shock propagation, right? And that's only one mechanism. There's other mechanisms for coherent radio emission. and we're seeing those, we think. All right, so next is, and I'll discuss this more, the ECM case in the case of exoplanets, because that's what dominates for exoplanets. So for the exoplanet case, the first radio planet was Jupiter. Bernie Burke and Ken Franklin built this Mills-Cross array in the 1950s to try to map extragalactic sources, and kept finding a bright source of noise in their data, which they initially thought was just a local farmhand driving back on a tractor every night. Eventually, they figured out it was moving sidereally, which most farmers don't do. And they established that it actually was, in fact, due to Jupiter. And that was a pretty important discovery because the radio emission was very bright. In fact, Jupiter can outshine the sun at low radio frequencies. And it was also the first confirmation that Jupiter has a magnetic field. And of course, that's a very robust field in and of itself, planetary magnetic spheric physics. And Juno is at Jupiter right now, making key measurements in that domain. And it was the first direct confirmation of Jupiter's magnetic field. And it was also the means by which Jupiter's rotation rate was established, because as you can see, the cloud belts have differential rotation. The field is anchored to the core and rotates with the core and has a clear periodic signal of about 9 hours and 55 minutes. And the reason you see this periodic structure is because the radio emission is very narrowly beamed. It's often said that Jupiter is the first pulsar before pulsars were discovered properly. Turns out that the Earth is also a bright source of radio emission, or auroral kilometric radiation. It wasn't actually discovered from Earth until the mid-60s, when we actually launched satellites above the atmosphere and flew them above the auroral regions. Why is that? It's not because the Earth's radio emission is not very bright. In fact, it's incredibly intense. It can outshine the terrestrial radar, for example, by a factor of 10 to the 4. The limitation is that the radio emission from the Earth is at much lower frequencies. And that's because the radio emission is the electron-cyclone maser instability, which traces magnetic field strength. It's produced approximately at the electron gyro frequency. And in Jupiter's case, that corresponds to magnetic field strength of 14 Gauss as the peak frequency. In the Earth's case, it's below a megahertz. And our outer atmosphere is ionized, the ionosphere, and radio emission below about 10 megahertz can't pass through that. So we just couldn't see it because of that effect. And in fact, when Voyager flew out to the giant planets, it kind of confirmed that every planet that has a large-scale magnetic field in our solar system has produced this bright radio emission that, as I mentioned, is the electron-cyclone maser produces highly circularly polarized and beamed emission close to the electron gyro frequency. And here I'm just showing the flux normalized to Jupiter's distance as a function of frequency. And you can see that only Jupiter extends beyond that cutoff of 10 megahertz, right? And it's incredibly bright. You know, Jupiter can be a megajansky. And Earth also is quite a bright source. The issue is that from the, Jupiter's radio emission, if I had a dipole here, I could pick it up pretty easily. For the rest, I got to go to space. That's the dichotomy we deal with planetary radio emission. What drives the radio emission from the solar system planets? In the Earth's case, it's just solar wind driven. It's the impact of the solar wind. You have day-side reconnection, nighttime reconnection, and that drives material into the upper atmosphere. And those electrons that are spiraling in the magnetic field generate this electron-cyclone maser emission. That also applies to Saturn and the outer planets, we think also. Jupiter is a different beast. Jupiter, you see emission powered by the movement of Io through the magnetic field. But also, that gives you the auroral footprint spots you see from Io, but also Ganymede as well in Europa. You also see another source of radio emission. Jupiter's emission is not actually powered by the solar wind. Plasma in the middle magnetosphere diffuses outwards, and the field is dragging it along. And as you move further out, eventually you have co-rotation breakdown. That drives a current system through the ionosphere, and that closes in the upper higher latitudes. And that's actually what produces the main auroral oval for Jupiter. And it's an immensely powerful power source of emission for Jupiter. In fact, in the infrared, emission from the thermosphere of Jupiter is regulated by this process. So can we detect this emission from exoplanets? And why do we care? Well, it would give us a way to measure directly magnetic fields of exoplanets and begin to go through the process of comparing field strengths of planets to atmospheric composition to understand better how important a role the activity of a star plays in atmospheric composition. We can measure rotation rate, and we can also provide insight into the internal structure. If you've got a magnetic field, you've got internal convection. And there's actually, today in the New York Times, a really nice profile of Maggie Kivelson, and it talks about how Galileo was able to confirm that Europa had a subsurface ocean by measuring the fact that it had a large-scale magnetic field that was giving you a probe, basically, of the interior structure.
Let me
Sure.
So in the case of Jupiter, as you pointed out, itself doesn't quite belong to the Earth category. On the
Right.
other hand, the moons do.
That's right.
The enemy is a lot like that.
That's right.
In fact, it shows a lot of the signatures as was seen by flybys.
That's right.
The question for exoplanet about which I don't know much is that do moons give you information?
Yeah. Oh, yes. And we had a recent. This week is the first announcement of a possible exomoon. I think you can generalize. Anytime you've got a magnetized or unmagnetized body moving through a magnetic field or a plasma, you potentially have a source of emission or a source of energy to produce this process. And I think you can generalize it. Typically, we think it's the Poynting flux ultimately that gives you the energy source. And in fact, we see a pretty tight correlation in our solar system between the output radio power and whatever your source of Poynting flux happens to be. In the Earth's case, it's the solar wind impacting the Earth's magnetosphere. So that cross-section of the magnetosphere and the energy of the solar wind is what gives you your radio power. In the context of exoplanets, that gives us hope, actually, because if you move, for example, Jupiter in by a factor of 10, well, then you get 100 times more radio emission, right? So we think there are populations that we can target where the emission might be a lot brighter. As it happens, I mentioned Jupiter is a megajansky. Well, it turns out stars are pretty far away, and most, in fact, observatory, which is, as I mentioned, is nestled between the Sierras and Inyo White Mountains in near Big Pine in California, and we wanted to basically observe at very low frequencies, between 20 and 85 megahertz, so we'd be able to find something like Jupiter. And most importantly, we want to do full cross correlation, which means that we combine the signal from every antenna with every other antenna. And that means you can image the entire field of view of the dipole, i.e. the entire sky. That is a really data-intensive thing to do. We produce about 10 petabytes of data per day, raw data, and our final data is about 50 terabytes per day. So it's not trivial, but the data is very homogeneous, and if you optimize, you can drink from that fire hose. And the goal is to image the entire sky every 10 seconds with about 5 arc-minute spatial resolution. Here's an example of the dipole that we use. It's actually a dipole we got from the original LWA, which is a telescope in New Mexico that beamforms like traditional dipole arrays do. Okay, what is we built the array in 3 stages. So here's stage 1. It's an aerial view of the Owens Valley Radio Observatory site. Here is the traditional big dishes we have on site, and here is where the stage 1 array was. And the stage 1 was to build just a compact core. So we built, in this compact core, we built 256 antennas. We buried about 88 kilometers of coaxial cable and power connectors, and we surrounded it by a kilometer of fencing. The latter because there are a lot of cattle that come to the valley, and our antennas are the perfect height to scratch their behinds on, so that's not very good for calibration, so we try to keep them out. On the southern side of the array, we have this big shipping container that we've fitted with electronics. There's about 50 kilowatts of electronics in here, including our analog and digital and computing hardware. And on top of this, we have this monstrosity of a HVAC unit because it's very compute intensive. And here again is a close-up of our antenna and front end. The backdrop is the Sierras. It's beautiful. So we have each of these antennas. We have a cable coming up through here, which is serviced by this board. And we send signals back in towards this central location. Here now is an aerial view of our array. Unfortunately, dipoles are not as impressive as big dishes, so you'll always see a drone shot of these arrays because that's the only way to make them look impressive. Here are some graduate students for scale. So here's kind of the kind of network of coaxial cables buried into the ground, and this is just our core. This is our inner 200 meters of the array. It goes out by a factor of 10 larger. Absolutely, yeah. Polarization is very important for the exoplanets, actually. So here is not an image of the radio sky. This is just an optical image to guide your eye to what you'd expect for the radio sky, i.e. the full hemisphere in sign projection, east, west, north, south. So I'm going to show you the first image from our core array. So this is what a snapshot image looks like from the core array. For those of you that don't know, the brightest source in the sky is not the sun. It's these two sources, Cassiopeia A, a young type 2 supernova remnant in our galaxy, and Cygnus A, which is this ridiculously close FR2 type radio galaxy. And we can remove those using a thing called direction-dependent calibration and peeling. And here's the resulting image. It's very pretty, shows the galaxy synchrotron very well. You'll note the absence of point sources. And that's because the array is too compact. We can't resolve out the confusion to see all the point sources we want to see. And that's why we moved to stage 2, which is to build our outrigger antennas. And the stage 2 actually was very difficult. We had to bury 40 kilometers of optical fiber and figure out how to use optical fiber instead of coaxial cable. And that was a major technology development we did in our group. Sandy Weinreb at Caltech has been phenomenal. He's built these fiber links that allows us to do RF over fiber for very cheap. To do it commercially, it would cost a few $1,000s per antenna. And Sandy just built us a new module, and we can do it for $100 per antenna now. So we built our first stage 2 array with the outliers, and that's going to have that has 32 antennas on these longer baselines. Now that's very sparsely sampled. Our stage 3 will have 64 more. Even though it's very sparsely sampled, it's still a good improvement. So we're actually at the science stage with the stage 2 array. So here now is an image of the entire sky with the stage 2 array. That's a 10-second snapshot of the sky, about 10,000 sources per 10-second image. And we don't just do images, we do movies. Here's a 3-hour movie centered on a long GRB. But you'll see, for example, airplanes flying overhead, and you'll see that's a crab pulsar pulsing. You see meteors hitting the atmosphere, and you'll see lots of other things that are going on. And there are stuff we want to get rid of, because our main focus is trying to do this exoplanet science. Oh, absolutely. In fact, I can kind of go back up and show you something. If you'll see like see this twinkling here? That's the ionosphere disturbance. It will move across the sky, and it will end up here in about 10 seconds. So we see clear. I mean, JPL are super keen to reconstruct the ionosphere above the array using using these sources. But for me, it's just a contamination. Right? So you can see up here now, they're all twinkling up here, and they're well behaved down here, because this disturbance is propagated across the sky. The ionosphere is by far the biggest challenge at these very low frequencies. It's pretty messy. And there's the crab again, pulsing away. Okay, so we don't just do Stokes I, total intensity, we do Stokes V, because exoplanets, or planets in our own solar system certainly, are highly circularly polarized. And we want to use this same effect to peel away the confusion of the Stokes I sky and look for pulsing planet sources in the same way we've done for brown dwarfs. Okay, so here's how it goes. We want to make light curves. So here's an example of light curves for the nearest 5 stars above the horizon at this particular image, which is these 5 right here. And the goal, and we've just started this survey now over the next few years, is to make light curves of the nearest 4,000 stellar systems, eventually continuously. Initially, we're doing surveys, but eventually, with the next upgrade, we'll be doing it continuously. Here's all the nearby M Dwarves above the horizon this time, and here are all the FGK dwarfs. So at each location, you make a measurement and you produce a light curve, and that's your space weather monitoring. And this is work by Marin Anderson, who's a graduate student at Caltech. And the goal then is to do this, and not just the radio. Our collaborators with the Every Scope, led by Nick Law and also Rob Quimby, they're also doing this in the optical with 8,000 square degree field of view. So that will give us some constraints on the flares as well simultaneously. So we'll have flares, and we hope CMEs, and eventually exoplanets with this data over the next few years. Our first 100-hour survey, we've just finished up. We're doing the analysis right now, so you'll see that pretty soon. And the goal here is to kind of, obviously TESS is going to find all the nearby transiting exoplanets. We want to basically build contextual information about the star to help interpret what we see in terms of atmospheric composition. And here's a very extreme case. We're a long way from this. But we'll start off, we hope, with the hot Jupiter population and so forth. Okay, before I finish, I want to just touch on some other topics. Given that I'm at the IAS, I want to touch at some other more theoretical things that we can try and do that are of interest here when you have an all-sky field of view, because it's not just exoplanets. We can do transients, cosmology, the sun, Jupiter, and actually cosmic rays. I'll do this very briefly. First up, transients, and right now we're doing a sky survey for radio transients. One thing we want to do is look for low-frequency prompt emission associated with LIGO or Virgo sources. There's lots of theory that speculate that you'll see a prompt or precursor pulse for comet object mergers. There was a paper, I think, last week by Maxim Lukatov about this. Of course, it's not as on firmer foundation as when you have stuff hitting stuff, giving you synchrotron radiation, and we've been working on that as well. But this is pretty exciting, because if it does exist, it provides you with a prompt and potentially precursor to correlate with LIGO signals as they come in, which I think is very exciting. So we've begun the process rather of developing our ability to do this. In fact, we were online for GW170817. But when I said we image all the sky all the time, I lied. We image half the sky all the time. We can't see through the Earth. And unfortunately, from Owens Valley, it was below the horizon. Here's an image from 12 hours before. Here's the Ur region. So we are ready to go for O3, and we will be observing continuously during that.
What is the time scale of that observation?
As in, like, the duration?
Yes.
Very well. Different models have different expectations. I know Maxim's paper proposes a slow ramping signal that would cut off close to the time of merger. Others predict a short, like FRB-like pulse, fast. So we want to try and explore both. One thing we want to do is be able to coherently beamform every single pixel in these images. That's a huge data challenge, but we're building that up soon as well. Of course, the sun is above the horizon at every daytime integration, and what we do there, the NGIT group are actually doing dynamic imaging spectroscopy, looking for a type 2 burst. And here's the onset of a type 2 burst right here. This student, Sherry Chabra, and NGIT has made this very nice movie, which shows how that compares to what you see from your SOHO optical CME data. So here is the radio corona of the sun at 2 frequencies, and suddenly you see it becomes dominated by this bright bursty emission. That's a factor of 1,000 brighter when it switches on. You can't see any of the source in the sky when the sun does this. And here we're showing the same exact data overlaid in contours on the optical SOHO image data, which is actually a movie. We're playing this at only a factor of 60 faster than real time. And you see, we see the shock developing from the type 2 burst